So we're going to look at two very related concepts. And somehow it seems that putting these two concepts in the same section and giving it these new names ends up being confusing. So this is going to sound more confusing than it actually is. I maintain that you know all of these things already. We're just kind of giving them different names. One of those things is linear approximations, and the other thing is differentials. So we'll learn how to compute the linear approximation to a function near a point, and we'll learn how to compute the differential of a function and use differentials to estimate changes in function values. Okay, so let's get started with the linear approximation deal. The big idea, what linear function best approximates a given function f near a point A? If you have the graph of a function and it's not a nice straight line, what straight line would be the best substitute for the curve near that point? Well, of all of the straight lines that you could use to approximate this function, which one would do it best? Yeah? The tangent line, of course. It says of course, right? Okay, so to find a function which is a linear function, b goes through the same point at A, and the thing we would use is the tangent line. Okay, so what's the equation for the line which goes through the point a comma f of a and is tangent to the curve at that point? Well, we know it goes to this point. What would its slope be? What is the slope of the tangent line through a comma f of a? The derivative of f at a. So the answer is that we need a linear function which goes through the same point a comma f of a and has slope equal to the derivative. So if you use, say, the point slope equation for that line, then what you get is an equation which looks like this: y minus f of a is the y coordinate of the point you go through, equals slope is f prime of a, times x minus the x coordinate of the point you're going through, that is x minus a. Okay, so this is really just the equation for the tangent line. We are giving it a new name. It's called the linear approximation to the function f at a, or near a. For different a's, we'll of course have different linear approximations. Okay. So that is the equation for the tangent line, which we'll give a new name. We'll call it the linear approximation. Here's the picture of what's going on. We pick the point A. Okay, we want our straight line to go through the point a comma f of a, but we want it to be a good approximation to the curved function f. Okay, so what we contend is that the linear approximation, the tangent line here, is a decent approximation to the function near the point. What that means is that if you look close to the point, you see that the red line and the blue curve are not that far apart. And in the pixelated drawing that I have, it looks like they're almost on top of each other. How good is this approximation? Well, the closer you get to this point A, the closer the linear function and the nonlinear function are getting. At A, they're exactly on top of each other, and close enough to A, they are close enough to each other. And you can guess that probably means some kind of limit statement, right? So the L of x function is a linear function, and it's a good approximation to the function, meaning that these are pretty much overlapping. Go a little bit further out, and it may not be so true. Out here at this point x, f of x is here, and L of x is here. They're kind of far apart at this point, but close by, they are close together. Okay, so let's do an example of this. We're going to estimate the sine of 61 degrees by using a linear approximation. We'll use two different ones. First, we'll do it around the point a equals 0, and then we'll do it around the point a equals pi over 3 or 60 degrees. We like radians, so we'll say pi over 3, but if you like to think in terms of degrees, all you have to do is multiply by 180 divided by pi. Okay, so we'll do the first one first. Linear approximation to the function sine of x around the point a equals 0. Well, if I look back at the formula, which is here, I need to know f of 0, and I need to know f prime of 0. Well, f of 0 is the sine of 0, that's 0. And f prime of 0 is the cosine of 0, that's 1. So the linear approximation looks like f of 0 plus f prime of 0 times x minus 0. And if you simplify that, it's just regular old x. So what this is saying is that this linear approximation to the sine function near the point 0 is L of x is equal to x. Now, if we use this linear approximation to approximate a value of the function, it tells us that the sine of 61 degrees, and 61 pi over 180 is 61 degrees in radians, is approximately equal to 61 pi over 180. L of x is equal to x, and f of x is approximately equal to L of x. All right, and if you plug that into your calculator, you'll get that 61 pi over 180 is 1.0646 pi. Okay. So comment on this approximation here. We've determined that the sine of 61 degrees is approximately 1.06. Is that a good approximation, or does it leave something to be desired? It leaves something to be desired. So what's your issue with the sine of this angle being approximately 1.06?
We use the reference point that's very far from
Yes. The reference point, I like that term, is 0 here, and we're approximating at 61 degrees. It's actually pretty far away from 0. And sine of 61 degrees is approximately 1.06. Doesn't really pass the smell test, right? What's bad about that? That's right. The range of sine is -1 to 1. So it's like saying, the square root of 3 is approximately -1. Okay, that's not even true. So, or saying that 3 squared is approximately -10. I mean, what we have is an answer. It's not even in the range of the function. So, this is not a good approximation. It's an approximation. It's like saying I made approximately $1 million last year. It depends on your idea of what approximately means. I didn't make anywhere near close to that. So what can we do instead? Well, let's try a reference point which is closer. For instance, 61 degrees is only 1 degree away from 60 degrees, and I know the sine of 60 degrees, so I'll use that to compute an approximation. So what is the sine of 60 degrees? I said I knew that, but do you know that? What's the sine of 60 degrees? Sine of pi over 3. Square root of 3 over 2. Yep. Okay. And the cosine of pi over 3? 1/2. Once I give you this one, the other one should be clear, right? Because this squared plus this squared has to be equal to 1. So square root of 3 over 2, quantity squared, is 3/4. 3/4 plus what equals 1? 3/4 plus 1/4 equals 1. So this would have to be the square root of 1/4. That is 1/2. That reminds me of another frequently asked question. What trigonometry do we need to know for the exam? If you open your book and before the title page, there's this like cardstock page of reference formulas. Look on those 2 pages. That has a nice crash course in trigonometry. And if you want more than that, read Appendix A. Okay. So cosine of pi over 3 is the square root of 3 over 2. I'm sorry. Sine of pi over 3 is the square root of 3 over 2. Cosine of pi over 3 is 1/2. And we can use this to get the linear approximation to the sine function near the point 60 degrees. It is f of a is pi over 3, plus f prime of a times x minus a. Okay? Different reference point, different linear function, different approximation. Question? Mm-hmm. Well, it's both. Okay? L of x stands for linear approximation. So its equation is the equation for a line, and we use the point-slope form to derive that equation. Okay? And so it is the equation of a line. It's the equation of the linear approximation function. Oh, yeah, so it's like y minus f of a equals m times x minus a. All right, and then I put the f of a on the right-hand side because I want to isolate the function. Okay, so if I use this linear function to approximate the sine of 61 degrees, then I would take the square root of 3 over 2 plus 1/2 times 61 pi over 180 minus pi over 3. So that's pi over 180 here, and you get 0.87475. And I don't know what it is exactly, or I don't know what my calculator would tell me that is, but that's probably a pretty good approximation. And at least it's less than 1, which is more than can be said about this approximation over here. So what's going on graphically? We have two different ways to approximate the sine of 61 degrees. What I want to know is how high does this, at what y value does the curve intersect that vertical line? Okay, the first method I used was to plot the tangent line that goes through 0, 0, and then follow it over here to 61 degrees. And this is my estimate for the sine of 61 degrees using that linear approximation. Does that look like it's close to the actual sine of 61 degrees? No, it looks pretty far off, right? If you know that this only gets 1 high, you can see that that's just way too high. So there's a big difference between that approximation to the sine of 61 degrees and the actual sine of 61 degrees. Instead, we'll make a different linear approximation at 60 degrees, which is pi over 3. We get a different line. And now when we plug in x equals 61 degrees, the red linear function and the blue nonlinear function are very close together. You can see that they're almost on top of each other here. Okay? And that's why this linear approximation is a better one, because we've chosen a reference point which is closer. Does that make sense? Okay. So when doing linear approximations, first of all, knowing how to write down the equation for the line is important, but also knowing the role of the reference point in the accuracy of the approximation is another big point. So here's another example. Let's estimate the square root of 10. Okay, it says estimate the square root of 10 using the fact that 10 equals 9 plus 1. Now, what is this a clue for? Well, we're doing linear approximations, so definitely we're going to take some function and make a linear approximation to that function near some point. So what function are we going to approximate here? What's the name of the function that we will want to find an approximate value for? What'd you say? Y equals 9? No, that's not a function. That would be a specific number. What function are we approximating? The square root function, right? We want to find the square root of 10. So if f of x is the square root of x, we want to estimate f of 10. Now, what's the role of the clue here? 10 equals 9 plus 1. What is that giving us a hint to do? We're going to use a as 9. Why would we use a as 9? Well, we're trying to approximate the square root of 10. And what is the square root of 9? Square root of 9 is 3. That's a nice number. Square root of 10, not so nice. So we're going to use a linear approximation to the square root function around a equals 9, and then plug in x equals 10 to get that approximation. Okay? That's the idea. So we're going to use linear approximation to this function near this point to estimate the square root. The whole idea is that the function should be approximately equal to its linear approximation. So f of 10 should be approximately L of 10. And L of 10, we're using the reference point a equals 9. So it's f of 9 plus f prime of 9 times x minus a, 10 minus 9. And now we just have to plug in what these things actually are. What is f of 9? It's the square root of 9. It's 3. And we chose a to be 9 because this was a nice number. What's f prime of 9? Well, we have to find the derivative of the square root function. But you guys know how to find the derivative of the square root function. It's just a power rule business. And you get 1 over 2 times the square root of 9. That is 1 over 2 times 3. And 10 minus 9 is 1. Okay, so if you add those fractions together, you get 19/6. And if you plug that into your calculator to get a decimal approximation, you get 3.1666666, etc. Right? It's 3 and a sixth. Does that make sense? Okay. So how would we determine whether that was a good approximation to the square root of 10, besides checking with our calculators and seeing what our calculator said? After all, the calculator is making an approximation of its own. Right? It can't tell you an irrational number. So how would we check this independent of a calculator? Yeah? we could graph f of x and L of x and measure the distance between f of 10 and L of 10. We need some really good graph paper for that. What would be another way to do this? We're trying to approximate a number whose square is 10. So if I have something which is approximately the square root of 10, what should its square approximately be? 10. Okay? So I will check to see if this is a good approximation to the square root of 10 by squaring it and seeing if it's close to 10. Now, to square 19/6, we square 19, and we square 6. So I'll square 19. The answer is 361. What's the square of 6? 36. Okay, so 19/6 squared is 361 divided by 36. Is this close to 10? Yes, it is, because 360 divided by 36 would be exactly 10. Okay, so the square is only a 36th off, which means that this number is pretty close to the square root of 10. Does that make sense? Awesome. Okay. So let's try another game that we can do where we can do arithmetic without using a calculator and without even using something like division. So let's say we've got some student, none of you, of course, would be afraid to divide 577 divided by 408. Oh, that's too complicated. Is there a way that I can get an approximation to 577 divided by 408 without actually dividing three-digit numbers? Well, yeah, there is. As a matter of fact, you can rewrite this fraction as this mixed number, right? Because the numerator is greater than 408, so you break off the 408. What's left over is 169 divided by 408, and I can factor out a 4 from the denominator here. And what I notice is that if I can just approximate 1 over the 102, I can find an approximate value for 1 over 102, multiply that by a fourth, that's 0.25, that's not too hard. Multiply that by 169, not afraid to multiply. Add 1, that should give me a good approximation of 577,408. Now let's, again, set aside why anyone would do this, but think about how you could answer the question this way. How can we find an approximate value to 1 over 102 without using a calculator? Well, again, we're thinking about approximations. So when the goal is to estimate 1 over 102, you have to think about that as f of x for some suitable f and near a reference point a for which f of a is somehow nice. Okay, so you got to think about a couple of things at once. But what do you suppose would be f of x if we're trying to estimate 1 over 102? What function is being applied here when we're taking 1 over 102? Right, the reciprocal function 1 over x. So 1 over 102, or f of 102, is complicated, but what a close to 102 has a nice f value? 100. Very good. So we're going to use the fact that f of 100 is nice and easy to calculate, and f of 102 should be close by to do a linear approximation. All right. So that's the goal. We're going to take f of x to be 100x, or 1 over x. We know f of 100. We want to know, or we want to guess, an estimate of f of 102. Oh, excuse me. The rule is if your phone rings, I have to dance. So. Again, that's going to be on the internet. Okay, so f of 102 is f of 100 plus f prime of 100 times 102 minus 100. So we want f of 100 is 100. F prime of 1 over x, let's see, 1 over x is x to the minus 1. So f prime of x would be minus 1 x to the minus 2, which would be the same thing as minus 1 over x squared. F of 100 then is minus 1 over 100 squared, and I'm going to multiply that by 100 by 2. So to estimate 1 over 102, I'll take 1/100th, and I'll subtract 2 10,000ths. And that gives me 98 10,000ths. Okay, and I did all of that without having to do serious arithmetic. So if I got this estimate for 1 over 102 and did the things that I said I would do over here, multiply it by 0.25, multiply it by 169, add 1 to it, I will get 1.41405. All right, and here I've actually run this through a calculator to see what the calculator says is this fraction. And in decimal form, it says 1.41422. So how good is our estimate? Actually, we have 3 decimal places of accuracy, which is not too bad for a simple linear approximation. Okay? So this is relevant, especially if you're programming a computer. Computers, in their circuitry, they can add and they can multiply, but the multiplication is really just by repeating adding. So all the computers can really do is add. Division is often done by doing some kind of approximation, especially when you have numbers with lots and lots of decimal places. Okay, so that's the deal with linear approximation. Questions? Yes? Okay, so before we got started with linear approximation, what we said was that 577 divided by 408 was 1 plus 169 times the fourth times 102, or 1 over 102. So if I can estimate this, then I just have to multiply by 0.25, multiply by 169, add 1, and that'll be my approximation. So that's what I did here. I took this number, multiplied by 0.25, multiplied by 169, and then added 1, and this is what you get. Okay, I did that behind the scenes, because I only have so much real estate there. Okay? So moving on from the idea of linear approximation, we're going to go to a different perspective. But I want to emphasize that this is the same concept with just different names and slightly different notation. So I'll warm up to this by asking a few questions. Suppose we're traveling in a car, and at noon, our speed is 50 miles an hour. So as a birthday present for my kids this week, we're going to Cocoa Key, which sounds exotic, but it's actually in Mount Laurel, New Jersey. So after class tomorrow, we're going to get in our car and we'll drive. And I'm sure that on the turnpike, I will hit a speed of 50 miles an hour. So just picture us driving down the turnpike at 50 miles an hour. At noon, we're going 50. And the question is, how far will we have traveled by 2 o'clock? What do you think? I didn't say that. I said estimate my position at 2 o'clock. But based on this limited information, what would your estimate be? A 100 miles, right? If I'm going 50 at noon, if I'm going 50 at 2 as well, or going 50 over the whole time interval, then I will have gone 100 miles. 3 o'clock, you can estimate that I've gone 150 miles. But what if I ask you how far I've gone by midnight? Is it as safe to assume that I've kept the same speed over a 12-hour time interval? No, not so much, right? Have you ever taken a long trip and calculated your average velocity? It's hard to go more than 50 miles an hour average because you do have to stop one way or the other, right? It's hard to drive 12 hours without stopping the car. Either something becomes empty or something becomes full or both. And so this is a decent estimate. This is also decent but not as decent estimate. And this is probably not a very good estimate because of the fact that we took such a long time interval. Make sense? So let me ask another question. Suppose our factory makes MP3 players and the marginal cost is $50 a lot. How much will it cost to make 2 more lots, 3 more lots, 12 more lots? Well, if the marginal cost is $50 a lot, you can probably guess that 2 more will cost about $100 more, or that 3 more lots would cost about $150 more. But 12 more lots, that's not as reasonable to say. It's not as likely, because the more that you make, eventually your marginal costs are going to increase. Why would that be? Well, at some point, after increasing production, you will probably have to either buy a new factory or pay overtime to your workers, and that's going to require extra investment. So these are reasonable estimates. This is not as reasonable. All right, so let's ask now a graphical question. Suppose a line goes through the point that has coordinates x0 and y0, and it has slope m. If you move the point horizontally by some distance dx, staying on the line, how far has the point moved vertically? Believe it or not, this is the same question that we have been asking in the previous 2 slides. We have a line that goes through some point. We know its slope. Slope's called m. we move it dx to the right, but it stays on the line, how far up or down does it move? You're not going to get an answer like 3, right? There's no numbers here, so the answer has to be in terms of the named but unknown quantities that are there. Yeah? M times dx. Think about that for a second. The slope of a line is defined to be the rise over the run. And if you know the run is some horizontal distance dx, and you know the slope is some number m, then you can solve for the rise. It's m times the run, right? Slope times the run, or m times dx. All right, so if you have a line and you want to estimate the change in y along that line, you can get it by taking the slope times the change in x. And that principle is rebranded the differential. Okay. So here's the deal with differentials. The goal with using differentials is to approximate the change in the function value, y, over a small change in the input, x. That is, we want to estimate f of x plus delta x minus f of x, that is the change in y values, over some small interval delta x. Now, what we said was that near the reference point for a linear approximation, the function and its linear approximation are approximately the same. So the difference in the function values for the nonlinear function should be approximately the difference in the function values on the linear function. Now, the difference in function values on the linear function, that's just another way of saying the rise. And you just told me that to get the rise, you can take the slope times the run. The slope is f prime of x, because that's what a linear approximation does. And the run is delta x. Okay, so that whole equation is just saying what we have already said before, that the linear approximation is an approximation to the nonlinear function. That is, the change in y's over the nonlinear function is approximately the change in y's over the linear function. And then we just start giving things different names. So delta y is the change in y's, and we'll call by dy the change in y's over the linearization function. Okay, and also we'll call delta x and dx the same thing. So if you look at the picture, what's going on here? I want to estimate delta y, that is the change in y values, the vertical separation between f of x and f of x plus delta x. That might be complicated because f is not a nice linear function. So let me substitute a nice linear function and instead compute the change in the function values on that linear function. That one is easier to compute because all I need to do is take the slope at this point times the run. All right, so delta y is approximately dy, and dy is by definition f prime of x times dx. We write it like this. Delta y is approximately dy. dy is equal to f prime of x times dx. And that looks a lot like this equation here, dy dx is f prime of x. Right? If I take this thing here and solve it for f prime of x, the dx goes under here, and I have this fraction equals this derivative. Okay? This is easy to remember because that looks like the Leibniz form of the derivative, and that looks like the Newton form of the derivative. These are supposed to be the same quantity. What have I done here? I've actually lied to you, or I've done something I told you not to do. Right? I told you do not treat the derivative like it's a quotient of two actual numbers. But today, when we're thinking about these differentials, it's okay to think about dx as a number and dy as another number, and the fraction of the two equal to the derivative. Okay? Dx is actually kind of like a variable, and dy is another variable, and they're related by this equation. Dy is equal to f prime of x dx. Okay? So anything which uses a differential is really just using linear approximations, but giving different names to the same thing. Now, why would we do this? Why would we make you learn the same concept with two different sets of notation? Well, you know, the mathematicians like to do it one way, and the physicists like to do it another way, and the chemists like to do it another way. And everyone's got their own sort of oral tradition of mathematical terminology. This is more of a physicsy way to do it. Okay, so let's do a couple of problems. the general process will be to estimate delta y for some function f. We will substitute dy because we can compute dy easily. dy is f prime of x times dx. Find out what f prime of x is, find out what dx is, plug it in, delta y is approximately that product. That's the basic idea. We'll approximate, differentiate, evaluate, then cogitate. Okay. So here's an example. A rectangular sheet of plywood measures 8 feet by 4 feet. I downloaded this picture of a piece of plywood just to demonstrate. So it looks, the ratio is 2 to 1, right? It's twice as tall as it is wide, or twice as long as it is wide. Plywood's made by a machine, and there's a saw that cuts out the rectangles. Let's suppose that our plywood cutting machine is defective, and it does cut rectangles to the right proportion, but not necessarily to the right length. So whatever the width is, it will definitely be half of the length. But if the length is not quite right, not exactly 8 feet, then the width will also not be exactly 8 feet, or 4 feet. And that means that the area won't be exactly the same as a regular area of an 8 by 4 foot rectangle. So the question I'm going to ask then is, if the length is off by 1 inch, how bad can the area be off by? If my plywood cutting machine is not calibrated correctly and it makes a rectangle which is too long, how bad can the area be from what it's supposed to be? Okay, so does everyone understand that question? All right, I've been shopping too much at Lowe's. Okay, so here's the idea. Our function that we're trying to estimate is the area function. Because the length of the rectangle is definitely the same as the twice the width, then we can say that the area is just a function of the length. That is, it's equal to 1/2 times the length squared. Let me go back to the picture to explain why that is. We know the length, and we know that the width is half of the length. So if we want the area, we're going to take the length times the width. That is, the length times half the length. That results in 1/2 the length squared. And what we know, we want to know what is the change in the area, that is how far off the area can be, when we're trying to plug in 8 feet and we might be off by as much as 1 inch. Okay, it's supposed to be an 8 foot by 4 foot rectangle, but it might be 8 foot plus an inch or 8 foot minus an inch. How bad is the change in area going to be? How big is delta A when A is this, L is 8 feet, and delta L is 1 inch? Okay, well, I'll do this 2 ways. One, just using the regular subtraction method, which I can do because this is an algebraic function. And then we'll see how differentials can get a similar answer. So the subtraction method would be to plug in L plus delta L, that is 8 feet plus 1 inch. And if you do the fractions, that's 97/12 feet. All right, 1/2 times 97/12 feet is 9,409 divided by 288. And what we want, that's square feet. So delta A is A of L plus delta L minus A of L. That is this fraction minus 32 square feet. And what I get is 0.6701 square feet. Okay? So by actually doing the algebra, we get this estimate for how bad the area can be. 67 hundredths of a square foot off. How would we do it instead using a linear approximation or a differential? We would do it this way. A of L is 1/2 L squared. So dA dL is just L. You see why dA dL is L? Because power rule says pull down the 2, subtract 1. So it's 1/2 times 2L. That is just L. All right, this is the derivative of A as a function of L. And if I want to write that as a differential equation instead, it's dA equals L dL. Now, I'm breaking the rules here, but we're doing things that physicists do, and they break the rules all the time, so that's okay. So dA is L dL. And what we said about linear approximations is that dA should be a good approximation to delta A. Delta A is the thing I want to know, dA is going to be easier to calculate. Because what is dA if L is 8 feet and dL is 1 inch? Well, we should compute these both in the same units. So L is 8 feet, dL is 1/12 of a foot. So dA is L dL, that is 8 times a 12th, that is 8/12, which is 2/3, and that's 0.667, or 0.6666667. Okay, so delta A, which we computed explicitly, is this guy. dA, which we computed using an approximation, is this guy. Are they close together? Is delta A approximately equal to dA? Yes, they are, right? They're only off by actually only about 3 thousandths. So not a bad substitute, considering it's how much easier it is to just take 8 and a 12th than doing all this fraction stuff. Okay? So the differential method allowed us to do a linear approximation, which gives us approximate values of functions. They're less approximate, right? But they're less accurate, but they are quicker arrived at. Okay. So why would we do such a thing when we could just plug it in and find delta A explicitly? Well, it's not always going to be true. Linear approximation is quick and reliable. Finding delta Y exactly is going to depend on what kind of function you have. We could do delta A explicitly because A was just 1/2 L squared. But what if A were L times sine of L? Okay? That would be much harder to estimate the difference in function values. But the derivative would not be so hard to estimate. And so we would be able to get the differential easier. And the more complicated those functions get, the better the differential method is as a substitute for explicit differences in function values. And I've got one example which makes that very evident. And sometimes we only have a limited amount of information about a function. For instance, again, to use a physics example, you'll talk sometimes about like a particle that's undergoing some force field, and all you know about the force field is that it's pulling things towards the center. And so you say, okay, well, this means that the force is, well, the potential is 0 at the center, and the derivative of the potential is 0 at the center, and the second derivative is positive. Okay. Now, that's all you know about it. Then the best you can do is make a linear approximation to the function. Sometimes you may only know a few bits of information about some function, but you can actually do some estimation using that limited information. Okay, so that's what linear approximations are good for. They can be used to find approximate values when you only have limited information. Think about how we were able to find the sine of 61 degrees as an estimate because we knew the sine of 60 degrees exactly. Okay. So here is another example. I say examples, but I'm thinking I only have one. Yeah, okay. So I have an example here for gravitation. So you guys remember, you saw the matrix, right? I have to be careful now because that came out when I was in grad school, which means it came out when you were in grade school. But eventually you did see the matrix, right? I saw it in the theater. You probably didn't. But there's that scene where Morpheus is showing Neo how to get out of the matrix for the first time, and he's about to plug something into the back of his head, and he says, this might get a little weird, okay? So this might get a little weird. It's okay. You don't have to copy this down. I just want to point out that this is another application of linear approximation. Okay? You got that? I'm ordering you not to take notes. Okay. Well, the process is that, the problem is that we're going to think about gravitation in two ways. The way that we usually think about gravitation is that it pulls on things with a constant force. That is, if I have a 1 kilogram ball and I go up to the roof of the Silver Center and I drop it, it's going to be pulled by a constant force until it hits the surface of the Earth, and then it's obviously going to stop. Okay? So that's one way to think about gravitational force, is that it's constant. Now, there's another way to think about gravitational force, and that's that not only is the Earth pulling down this ball, but the ball is pulling on the Earth a little bit. Okay? And so there's a force between these two things, which is proportional to the mass of the Earth, the mass of the ball, and inversely proportional to the square of the distance between them. This is what Newton figured out ages ago. So if you think about the ball as not just falling towards the Earth, but about the ball and the Earth pulling themselves closer to each other, or pulling each other closer to themselves, or something like that, then the force would not be a constant. It would be a function of the distance between the ball and the Earth, and it would be negative constant times the mass of the Earth times the mass of the ball divided by the distance between them squared. Okay, and when we say the distance between the ball and the Earth, we really mean the distance between the center of the ball and the center of the Earth. Now, if you plug in this equation to the... I said stop taking notes. I didn't say stop listening. When you take this equation, you plug in the radius of the Earth, that is, when the ball is actually on the surface of the Earth, then what you get is the force at this radius of the Earth would be this constant, whatever it is, times the mass of the Earth, times the mass of the ball, divided by the radius of the Earth squared. And that's where this little g comes from. It's actually the big gravitational constant times the mass of the Earth divided by the radius of the Earth squared. Okay, so this is the force that acts on the ball if it were actually at the surface of the Earth. What we're doing by this model up here is assuming that this constant value is the same at all heights. All right, so this is an approximation to this function. To say that the force is constant is an approximation to the actual Newton's gravitational law. Okay, and we do this all the time. Remember last time we were talking about the van der Waals formula? We had said there are ideal gases, or we can think about the ideal gas law and then the non-ideal gas law. It depends on how complicated you want to get, right? So we can be simple or we can be complicated. The question is, how different is it to be simple than to be complicated? How much accuracy are we giving up by substituting this constant gravitational force for the non-constant gravitational force? Okay, so what is the maximum error in replacing the actual force felt by this constant force at ground level? Okay, and we can ask many variations on that. What's the maximum error, relative error, percentage area, etc. Okay, here's the answer. What we have is that the force at the radius of the Earth is m times g. And we want to know what is the change in force between radius of the Earth plus a little bit minus the force at the radius of the Earth by itself. Okay, that's delta F. We can substitute for that dF, and dF we can get by taking f prime of r at r sub e and multiplying by dr. Now remember, this could get a little weird. F of r was g times m divided by r squared. That's like g times m times r to the minus 2. So you can use the power rule to find the derivative. And you get 2 times g times m times r to the minus 3. So f prime at the radius of the Earth is 2 gmm divided by radius of the Earth cubed. And we're going to multiply that by dr. But because we know that g times m divided by radius of the Earth squared is mg, then we can rewrite this expression as mg times the change in r divided by the radius of the Earth. That is the height of the building divided by the radius of the Earth. Okay, and what do you think about the size of this fraction here? Take the height of the silver center and divide it by the radius of the Earth. Probably going to be a small number, right? And that is the relative error in this approximation. Well, negative 2 times that fraction. Yes? That's a good question. Why do we have the dr down here and up here? Is that what you're saying? Yeah, well, this dr stands for the actual number that we are changing r by, and this dr is part of the derivative df dr. Somebody is really wanting to get my attention. I'm not available. Okay, so here's the derivative, and this is the number dr. So the relative error, that is the change in f divided by f, is negative 2 times the change in radius, that is the height of the building, divided by the radius of the Earth. So what is the radius of the Earth? If you go to Google and you type in what is the radius of the Earth, it tells you that it's 6,378.1 kilometers. And we know we decided that the silver center is 50 meters high. So if we divide those two things in the right units, what we get is that the relative error is 1.5 times 10 to the minus 5th. That is 1.5 times 10 to the minus third percent, 0.00156% off. So not a big deal in substituting the constant gravitational law for the inverse square gravitational law. So thank goodness. Okay. So like I said, that's not the kind of thing that I would make you do on a test. But what I wanted to show is that linear approximations are used a lot to estimate when on this particular scale, the difference is not that much. You know, if you want to measure your weight, you're basically measuring how much gravity is pulling you down, but you know, the scale is you are pulling on the scale as much as the scale is pulling on you. So, you know, that's an estimate as well. Okay. Next little example here. You can do more than one linear approximation to get an even better approximation to a specific value. For instance, we know that the square root of 2 is not a rational number, but let's go ahead and find a rational number that approximates it. So we'll get that by taking the square root of 2 and finding, you know, f of a number close to 2 for which, we want an a close to 2 for which the square root of a is nice, and so the estimate will be good. So one number which is close to 2, which has a nice square root, is 9/4. Is that right? Well, 9/4 is 8/4 plus 1/4, and that's 2 plus a fourth. So that's pretty close to 2. And the square root of 9/4 is just 3/2. So that's a good place. Good number close to 2 whose square root is rational. So we can use the square root function around the point a equals 9/4 to estimate the square root of 2. Let's go ahead and do that. So if you want to do it this way, this is f of x. That is x minus 1/4. So this is f of a, square root of 9/4. And this is f prime of a, 1/2 times the square root of 9/4. And this is x minus a. 2 minus 9/4 is negative 1/4. And if you do that, you get the approximation 17/12. Right? So the square root of 2 is approximately 17/12. So how would we know that that was a good estimate? Well, remember, we can just square it and see if we get a number that's close to 2. So I'll do the numerator. You guys do the denominator. What's the square root of 12? 144. 17 squared is 289. So 17/12 squared is 289 divided by 144. Is that close to 2? Yes, it is. Right? It's only off by 1/144. Okay. So what have I learned? Well, now I know another point close to 2 whose square root is rational. So instead of taking 9/4 as my a, I can take 289 144 as my a. So I can do another linear approximation using a is 289 144. So I've got f of a plus f prime of a. F prime of a will be 1/2 times the square root of 289 144. That is 1/2 times 17/12. And that's another rational number. It's 577 divided by 408. Now, neither of us know the squares of these guys. So if we plugged it into a calculator, we would get that 577 divided by 408. That's familiar. Have we ever encountered that fraction? The square of it is 332,929 divided by 166,464. And if you look carefully, you see that if you double the denominator, you get the numerator minus 1. So yes, that also is very, very close, much, much closer to the square root of 2 than we had before. Okay? Now we know another number whose square is very close to 2, so I could do yet another linear approximation and get an even better linear approximation, and so on and so forth. This method is called Newton's method. Basically, you're iterating a process by which you can get as close as you want of a rational number to the irrational number square root of 2. Graphically, what's going on is that we've got the square root function. We want to know f of 2, but that's irrational. Find a number close by, like 9/4, that has a rational square root, and follow the linear approximation back to x equals 2, and that's a good approximation. Okay, 2 comma 17/12 is my linear approximation. Should be close to f of 2. Blow this up and use the 17/12 squared as another a around which to approximate the function. Okay, so I would draw another tangent line, and that will give me another linear approximation. And you could repeat this ad infinitum to get as close as you want to the square root of 2. Okay, so what have we done? We've done linear approximation. We've done differentials. I want to emphasize that these are the same thing as plotting the tangent line, which you all know how to do. Linear approximation can be used to approximate the value of a function. So the linear approximation at a is f of a plus f prime of a times x minus a. Differentials, this is f of a plus of x, sorry. This is f of a minus f of x, and this is f prime of a, and then you multiply it by x minus a. So it's the same thing, all right? And don't buy plywood from me, because you know my plywood cutting machine is defective. Okay, so I'm finished. You have an extra, let's see, 13 minutes to frolic with your friends.